Welcome everyone. I am Roberto Luna, Senior Developer Advocate for Valkey at AWS Open Source. Today, we're talking about two of the hardest problems in computer science, naming things and cache invalidation. And I want to show you how one project got both of them right from the day one. Its name is Valkey. It's an anagram of key val, as in key value store. So the name is spot on. And what it does best is caching. Sub-millisecond rates, hundreds of thousands of requests per second. Valkey nailed both hard things right out of the gate. Phil Cantu said this nearly 30 years ago, and doing both of these things at scale right now in the cloud compute area, it's even harder. Let's explore how we can try to make our lives easier. But before we dive into strategies, let's make sure we are all on the same page about what caching actually is. Caching is storing a copy of your data that you access frequently in a fast layer, like Valkey, so you don't have to go back to the source of truth every single time. We can see this from DNS all the way to microchips in L1 and L2 cache. Without a cache, every request hits the database in this case at about 50 milliseconds on average. With a cache, most requests get served under a millisecond. The database only gets hit on a cache miss. The first time someone asks for the data, it's a simple concept, but as we will see, the devil is in the details. Valkey is an open source BSD high-performance key-value data store that supports a variety of workloads such as caching, session store, message queues, leaderboards, streaming, and can even act as a primary database. The project is backed by the Linux Foundation, ensuring it will remain open source forever. Valkey, it is a community fork that happened when Redis changed its license back in 2024. The same developers that worked on that project created Valkey. It's the same protocol, same data structures, same client libraries. If you have ever used Redis, you already know Valkey. Everything I show you today works with any Valkey-compatible data store. By the end of this talk, you will have 3 concrete things that you can take back to your team. Not theory, I already did that part. Instead, actionable items that you can start using tomorrow morning. These numbers come from real research. Twitter's Pelican team published that 30 to 60% of cache entries are never read a second time before the key expires. That is memory that you're paying for that does nothing. And poorly named keys? In our workshops, we found teams storing the same data under 3 or 4 different key permutations. That is 15 to 25% wasted storage right there. And there is thundering herd. When a popular key expires, hundreds of clients miss the cache at the same time and all hit the database. That spike slows down the database down and causes timeouts, which causes retypes, which adds even more load. It is a snowball effect that can take down your entire backend in seconds. Let us start with what we think our cache actually looks like. Clean, simple, and elegant. The client hits the cache, gets a fast response, cache miss falls through to the database, takes the stuff. This is a happy path that every diagram on every architecture shows. But raise your hand or say it on the chat if your production cache actually looks like this. The point is, this is the lie we tell ourselves. Let me show you what actually looks like. Here's the reality. Raise your hand or say on the chat if you have ever grabbed your codebase and found 3 different naming patterns for cache keys pointing to the same entity. That is the talk. 4 keys for the same user in this case. User in lowercase colon 42, user uppercase colon 42. That is case sensitivity bug. User underscore 42 underscore B2. That is a legacy format that nobody cleaned up. User misspelled USR colon 42 colon profile was never wired into the invalidation path. The database is groaning because every hit on the stale key triggers a fallback query anyway. Your cache is not helping, it's lying to you. So the cache becomes a liability instead of an asset. Every one of those stale or duplicate entries is a bug waiting to surface at 3 a.m. Let us talk about how we got there. There are 5 common mistakes that compound on each other. Mistake number 1, no key naming contract. Without a shared convention, different services or even different developers on the same team generate different keys for the same data. You end up with user lowercase colon 42 or user capital U colon 42 and user underscore 42, all pointing to the same record. That is the duplicate storage that we talk about and wasted memory. Mistake number 2, TTL as your only invalidation strategy. A fixed TTL means your data can be stale for the entire duration of that window. And when thousands of keys share the same TTL, they all expire at once. That is a thundering herd that we just talked about, and we'll dive deeper a little bit more later. Mistake number 3, Cache aside everywhere. In cache aside, the application reads from the cache, and on a miss, it fetches from the database and then it writes back to the cache. The problem is on the write path. If two clients update the same record concurrently, you get a race condition where the cache ends up holding the older value. The last write to the cache wins, and it might not be the last write to the database. Mistake number 4. No observability. If you are not tracking hit rate, eviction rate, and memory fragmentation, you have no idea your cache is helping or hurting. Memory bloat from orphan keys grows silently until you hit max memory limits and starts evicting hotkeys, which causes a bigger problem. And mistake number 5, no invalidation graph. When a product changes, you need to invalidate not just the product key, but every cache view that includes that product. Search results, category pages, recommendation list. Without a graph of those dependencies, you get cascading stale data across your entire application. These 5 mistakes compound if you cannot name your keys deterministically. Mistake 1, you cannot build an invalidation graph. Mistake 5, that is why naming and invalidation are kind of the same problem viewed from 2 different angles. And before I show you how Valkey solves invalidation, we need to be precise about naming, because bad naming is upstream for every invalidation failure you will ever debug. This grammar gives you 5 segments. Namespace is your service boundary. Entity is the data type. Identifier is the primary key, and the qualifier and version are optional but powerful. The qualifier lets you scope to a specific attribute, and the version lets you evolve your schema without breaking consumers, just like you version your APIs. Notice that good examples are self-documenting. You can read them and know exactly what data they hold. There are good keys and bad keys on this slide, and one of the bad examples is using environment on the key. Instead, use a different Valkey instance. These rules are non-negotiable. Lowercase only, because case bugs are invisible until you hit production. Use colons as separators because they play nicely with cluster hashtags, and scan match patterns using a glow pattern. Namespace first, so you can do scan using the glow pattern without scanning the entire key space, and also version your keys. You will not ship a REST API without a schema, so do not ship a cached key without one either. And I talk about hash slots, and cluster. Let me tell you a little bit about that. Valkey cluster uses a slot-based architecture to distribute data across nodes. The cluster divides the key space into 16,384 slots. Each slot is assigned to a specific node in the cluster. When a key is accessed, its slot is determined using the CRC16 hashing of the key. This is deterministic mapping, ensuring consistent data location across the cluster. Its slots enable horizontal scaling, and new nodes can take ownership of slots from other existing nodes. If a node fails, its slots can be reassigned to other nodes for high availability. That slot distribution is what makes Valkey cluster able to handle large datasets and spreading them across multiple machines, providing high availability as well. In this case, we have the user column 1 to 3 that yields into slot 12,893 that points to node C or shard C, the third shard on our cluster. Given the hashtags are critical in cluster mode, the curly braces tell Valkey which part of the key to hash for slot assignment. Group by identifier, like SQ-82917, when you need atomic operations across related keys. But be careful, if you group by entity like product within curly braces, all of your products land on the same shard, which can become a hotspot. Think about your access patterns before choosing your hashtag strategy. Ship this code snippet as a shared library and enforce it in code reviews. Your future self debugging at 3 a.m. will thank you. We have a Valkey key builder that takes an entity, identifier, and qualifier into the key name to make it deterministic. Notice that the composite identifier example, the list of SKUs gets sorted before joining. This is critical for determinism. Without sorting, comparing SQ-100 versus SQ42 will produce a different key than SQ-42 versus SQ100. It's the same data in 2 cache entries. That is the kind of duplicate storage that silently eats your memory budget. These are the 5 anti-patterns I see most often. The environment in key 1 is specifically common. Teams put prod or dev in the same key, which means the same code produces different keys per environment. Use separate Valkey instances instead. And the serialized query key, that doesn't work, where you have a predicate, in this case, where A equals 1 and B equals 2, is not the same string as where B equals 2 and A equals 1, even though they will return the same data. Instead, hash the canonical form. This is one of the most common mistakes I see in production. Teams serialize an entire object, sometimes 50, 100, or even 800 kilobytes of JSON, into a single bulky string key. Then, one field changes, like a price update, they have to do a full read, modify, write cycle. Get the blob, deserialize it, change the field, serialize it back, and set the whole thing again. That round trip can take about half a millisecond and sends over 2,000 bytes across the network. But the real problem is the race condition. If two clients do that read, modify, write at the same time, the last one to set wins and silently overwrites the other client's change. That is data loss bug that is almost impossible to catch in testing because the window is about 2 milliseconds when it happens. Now compared to a bulky hash, hset lets you update a single field atomically. No read, deserialize, and serialize, no race condition. The price update becomes one command, hset, key, price, and the new price. That is in a few microseconds and only 70 bytes on the wire. Nearly 7 times faster and about 27 times less network traffic. And here's the invalidation win. With a mega key, any field change means that the entire cache object is stale and you have to invalidate it. With a hash, changing the price does not affect the name, description, or the stock count. You eliminate the invalidation blast radius entirely. If you're doing get, deserialize, mutate, serialize, and set, you don't have a cache. You have a slow database with extra steps. Now that your keys have a structure, let's talk about when to throw them away and, more importantly, how. These are 4 strategies that you will choose from. They are not mutually exclusive. In production, you will layer them. TTL is always your safety network. The question is, what you put on top of it. Let's look at this decision tree. How critical is data freshness for your use case? If hours are okay, let's say static content, feature flags, configurations, TTL with jitter is your best choice. Lowest complexity always is your baseline. If minutes are okay, let's say a product catalog, user profiles, that means you can take advantage of an event-driven approach. Chain data capture streams or PubSub, and your cache stays fresh within seconds. No cache logic on the write path. And if you need seconds or immediate cache changes, let's think about financial systems or inventory or even authorization tokens, the write-through or write-behind approach will be the best choice. Write-through is the database plus the cache updates synchronously. That provides a strong consistency. And the write-behind writes to the cache first, and then the database asynchronously. This is faster, but there is a small data loss risk on a crash. The second question that you have to ask yourself is, are there any related keys? If yes, let's think about that product on the search, right? So we talk about when you make a change in a product, and then that's in several categories and product recommendations. Then you need to take advantage of a tag-based approach where you have a collection of similar keys that are related to this initial key. If you don't have any related keys, then you can simply just unlink that key and be done. We talked a little bit about the thundering herd. Let me explain what that is. When a popular cache key expires, every request that was hit in the cache now hits the database simultaneously. The database gets crushed, latency spikes, clients time out, and retries pile on top. This is a full outage to happen within seconds. How can you avoid and take the strategy of using the TTL plus jitter? Let me walk you through this code because both techniques are here. The first block, using the jitter, you have a base TTL plus minus 600 seconds. That means that keys expire between 50 and 70 minutes instead of all at exactly 60 minutes. One line, synchronous expiry eliminated, and fixes the thundering herd problem. The second block, xfetch, on every read, check how close the key is to expiry. A random value weighted by delta, the last recompute time, and a beta that increases probability as the TTL shrinks. When it exceeds the remaining TTL, recompute early. So hotkeys with thousands of reads per second will always have someone recompute that expiry. The cache never gets cold. The beta tuning, you will have to play around. 1.0 is the optimal default. The higher the value, recompute earlier. This is useful for expensive recomputes, for example, fetching from a cold storage or an analytical database. You can use a lower value to let the keys sleep fuller, closer to their TTL. You can use this for cheap recomputes or one-hit wonders. The takeaway is that jitter is the floor. Always use a TTL unless you really don't want to. Xfetch, on top of that, for hotkeys, that means that your cache expiry becomes a non-event. These charts tell the whole story. The red bars, when there's no jitter, about 5,000 keys expire simultaneously at T plus 3600. Every client misses at once, so up to 5,000 queries per second hit the database in under a second. The pool saturates queries queue, cleans timeout, retries Ballon, and there's a snowball to outage effect. The blue bars, with jitter plus minus 10 minutes, spreads 5,000 operations across a 20-minute window. The database sees about 200 queries per second, and it barely notices. The implementation is fairly simple, one line. Expiration equals to 3600 plus a random value between -600 plus 600. The jitter smooths the curve, and Xfetch kills the miss. For hotkeys, probabilistic error recomputation means that the cache never actually gets called. Once the request refreshes before expiring, everyone still hits. The result is that jitter plus Xfetch provide up to 99% reduction in redundant database calls. The second strategy is an event-driven invalidation that decouples the write path from the cache. The application writes to the database, and a changed data capture stream like Debezium picks up that change, and an event processor deletes the stale cache key. The application never has to know about cache invalidation, it just writes to the database. This is powerful for teams where multiple services write to the same data. The key thing to notice is that the event processor can reconstruct the exact cache key to delete because we have a deterministic naming taxonomy. Without that taxonomy, the processor will need to scan the key space or maintain a separate naming. Both of these could be expensive and fragile. Let me walk through to both sides of this code. First, the publisher. In the write path, the database commits first to the source of truth, then publishes a JSON event to a Valkey pub-sub, providing the action, entity, type, ID, and the change fields. The subscriber, the invalidation worker, parses the event, reconstructs the exact key using the Valkey builder, the Valkey key builder, and calls onLink, and removes it from the key space immediately and reclaims memory. No scan, no lookup table. The key is reconstructed deterministically from the event payload. This is a payoff of having that naming taxonomy. Invalidation becomes mechanical. And watch out, pub-sub is a fire and forget. So if the subscriber is down, the message is lost. In production, add a TTL always as a safety net underneath. Or swap the pub-sub mechanism for a more durable transport, such as Valkey streams, Debezium, Kafka. It's the same pattern, just different delivery guarantees. The third strategy, write through and write behind. There are two different patterns, but the same family. Write through is synchronous. The cache is always consistent, but writes are slightly slower, as slow as the database is. The write behind is asynchronous, blazing fast writes, but there is a window where the database has not caught up, and so you have to choose based on your consistency SLA. Financial data, write through, always. Build counters, write behind all day, no problem. The write through, the ACK goes back to the client only after the database confirms it is persisted. In the write behind, the ACK goes to the application immediately after the cache write, and the database gets updated asynchronously. That red line on the diagram below is your risk. If the Valkey crashes before the async write, you may lose data. So know your trade-offs. Strategy 4, tag-based invalidation. This is all of members. That means the number of members that tag particularly holds, not all of the key space. So you're not scanning millions of keys. You are doing an S members on a small set. That means the collection. This is how you invalidate all the cache views that contain the specific product without touching anything else. For example, On a news website or an e-commerce platform where a product is out of stock, you have to invalidate the categories and it belongs to, as well as trending products, etc. To invalidate by tag method, fetches all keys associated with a tag, deletes them in a pipeline using onLink for not blocking deletes, and then it cleans up the tag itself. One product change, one call, all related cache entries gone. Clean and predictable. Everything I show you is theoretical until you put numbers on it. Let us benchmark. This is our test environment. Valkey 9.0 on a Graviton3 instance, 1 million keys and 80% reads, 20% writes on the workload. All commands to reproduce these are in the appendix and you can run them yourself. The results are, look at that cache hit row. 0.21 milliseconds at P50, 412,000 requests per second. Now look at the miss row. It is basically the same as hitting the database directly. The entire value of caching is in the hit rate. A cache miss costs you the same as no cache at all, plus the overhead of checking the cache first. That is why hit rate is the single most important metric to monitor. Look at the hit rate difference, 62 versus 97.3%. That is a 35-point gap cascades into everything else. The naive cache sends 12,400 queries per second to the database in steady state. The optimized sends 1,850. During the burst, like a mass TTL expiry, the naive cache hammers the database with up to 48,000 queries per second. The optimized one barely twitches at 2,100. That is the value of getting naming and invalidation right. The time, cost, and carbon emission reduction is not magic. It is the compound effect of no duplicate keys, no stale reads, causing retry storms, no thundering hurt, and 56% less memory waste. The greenest query is the one that you never set. The purpose of this talk is to get you to that green line. This is your cheat sheet. Print it, pin it to your monitor, send it to your colleagues. The key thing is at the bottom, combined with. These strategies layer on top of each other. TTL is always your floor and you should always use it. Event-driven and write-through both benefit from a TTL safety net, in case the invalidation message gets lost. Tag-based works best when triggered by events. In production, you will use 2 or 3 of these together. Naming and invalidation are not two separate hard problems. They are one really hard problem viewed from 2 different angles. Get the naming right and invalidation becomes mechanical. Get the invalidation right and your infrastructure costs drop significantly. Valkey gives you every primitive you need. The hard part was always the design. And now you have a blueprint to take these things back to your team tomorrow morning. Let's take a quick look at a real-life example. This is a very simple application that has an airport database where we have flights and we can take advantage of seeing passengers, the manifest of the whole flight, and all of the details of the passengers. So let's just go and try to get data from the flight, in this case flight 115, and we can see that we take about 3.3 milliseconds. If we try to get it again, we see that now the data we get it from the cache. And that is a significant difference from the database that it was about 3.3 milliseconds versus 0.2 milliseconds. So if we try again, we can see that we consistently get sub-millisecond response times. Now, if we try a different table, or in this case, a different query that has multiple tables, we get the manifest, and that takes about 8 milliseconds. If we try it again, we consistently get sub-millisecond response times getting the data from Valkey. If we now try an even harder query, doing 8 table joins, we get a response of 1.5 seconds. That means that we probably are going to benefit even more from using Valkey, where the responses are still about a quarter of a millisecond, so significantly faster. And as we can see, we're speeding up our system up to 2,000 times by taking advantage of the cache. Of course, this is if we have very small data sets, which in this case, we probably do not. This database is about 4 gigs. If we flush the cache and we query the backend data store, we're going to get faster response time than the first time because now we have data on the buffer pool cache. But if we query from Valkey, we still get a lot faster response times. That means sub-millisecond, about 0.2 milliseconds. So we're about 4.5 times faster. If we get a more complex, it is still actually a lot faster than the last time. Last time was about 8 milliseconds. Now it's about 2. Nonetheless, if we continue getting the data from Valkey, we're consistently getting sub-millisecond response times and still over 5 times faster. For the most complex query, where we're doing 8 table joins, we already have the data on the buffer cache. Nonetheless, the response time is about 12 milliseconds. If we get it from Valkey, it's still 0.25 milliseconds. So that means that the most we get these frequently accessed data, because it will, in this case, the manifest will only change if the passengers do not check in or do not make it to the flight. That means it is going to be very uncommon. Most of the time, you're going to be using the exact same data. As you can see, we are speeding up our system about 18.6 times. And the more different queries you have, like we saw before, we got these even higher. These are some of the resources that you come back to reference Valkey. And these are some of the commands that we use on the benchmark. Thank you for your time. My name is Roberto Luna Rojas. I am a senior developer for Valkey, so please get in touch with us. Go to the Valkey.io website, join the Slack community, and happy caching.